Okay, can you hear me well? Yes? Okay, good morning, everyone. So let's start with the last lecture. Um, so I was in the process of discussing what I think is the simplest or one of the simplest um, um, examples of applications of bootstrap to effective field theory. All right, and we were discussing this system where we're interested in computing the potential or vacuum energy of a very long flux tube of pure glue that stretches uh, between two very heavy quarks. So you may think about uh, Young-Mills theory as UN with the mass of these guys well above the confinement scale. And what we said yesterday, quite quickly, is that we could describe this theory, okay, for the action of the wall sheet, where this was the induced metric, okay? So this is equal to the determinant of H alpha beta, okay? Where H alpha beta, if we go directly to the so-called unitarity gauge, it looks like so. So let me very quickly review, perhaps using different words than yesterday, what I said. And remember that we have as many fields. So these are coordinates of sigma in this notation. These are scalars of that are functions of sigma, space and dimension. And remember that we had as many as orthogonal directions, xi, xj, right? That was the setup. So these are just scalars, normal scalars with a vector index, all right? So the EFT is like the EFT of it's an EFT for spontaneous symmetry breaking of Poincaré, and it's quite analogous to the Pion EFT, and we need to start building invariants, and we saw that Ricci was a total derivative, so it does not contribute to initial observables. Then the next one we could write was built out of the extrinsic curvature and was zero by the equations of motion. And then the leading term that we could write had four powers of k, and there were two such contractions, okay? And these guys had 8 derivatives, okay? So very soft. Dot, dot, dot. And these are the coefficients. These coefficients depend on the details of the confining dynamics, all right? While the rest is simply fixed by symmetries, right? And we were drawing this analogy that you may think of this as the leading term in the Pion action. This is only an analogy, which is fixed by symmetries. And then we have the low energy constants, say L1 and L2, with 4 derivatives, which is the leading term that depends on the details of the confining theory, UCD, right? Except that here, the leading soft term has 8 derivatives, okay? Now, this, the universality that we observe here at the level of the action translates to the observables. So we're describing this, this vacuum energy of this object as an expansion, okay? So at large distance, it grows with the distance, and then we have 1 over r corrections, okay? And actually, the way I was writing it yesterday, which perhaps is even more intuitive, is to write first let me write this because a couple of persons asked me after the lecture, let's first write the effective potential, which is the vacuum energy density, as a function of the radii, all right? So at the leading order, we have the cosmological constant, which is simply this piece from the action, all right? Next, we have a loop from the free theory, okay? And this loop So you see, you can do it by power counting analysis. It has two derivatives of x, okay? So use like 1 over r squared, okay? And there is some constant here that counts the number of degrees of freedom, which is d minus 2, okay? This sometimes people call it the Casimir energy, or in the context of lattice, people call it Lucier term. There's some exact factor which we can write down, which actually I'm not sure I have it here. I think is a 6 pi d minus 2, but I'm not 100% sure about this 6. It may be a 3, okay? It's in the notes. I mean, I'll give you the exact formula in a moment, okay? So this in thermal field theory would be simply this vacuum loop, right? It's clear to everyone what I mean? And now we compute loops, no? So the next piece, so maybe I can give you the exact formula right away. So the exact formula is equal to BF R times R, okay? And it's given by this. It's R squared minus pi over 3 d minus 2, okay? So let me comment 1 second on the exact formula. All right, so the next piece here is 2 loops, okay? So it's simply R4 here, okay? And then we have 3 loops, which is R6. So there are here some calculable coefficients, okay? And here we will have Elias square, which comes from this vertex. So this is simply kinetic term square, okay? And comes from the first order expansion of this guy is squared, okay? So we have one insertion of Elias, the vertex, which is what I wrote here, okay? One insertion of Elias square. And then we have 3 loops, okay? So diagrams like this, okay? So we have an Elias 4 here because of the 2 insertions, plus dot, 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 okay? And now here enters the first leading non-universal term, which is going to come from an insertion of this guy, okay, in the vacuum, which is this piece, okay, plus some number of loops coming from Nambu-Goto, okay? So the vacuum energy is fixed by symmetries up to powers of 1 over r to the 7, okay? The reason the 7 is observable is because this can be measured in the lattice, okay? So in the, I think I wrote it somewhere. I'll give you the numbers in the lattice here. Give me a second. There's some normalization involved. I'm not sure I have it here, but in the lattice it has been measured for d equal 3, all right? Now, this d delta, in general, we can compute it, and it's given by the following equation. Is 32 pi 6 over 2 to 5, 2 minus d, d minus 2, alpha 3 plus d minus 4, beta 3, okay? Now, G1 is proportional to alpha, and G2 is proportional to beta. There's some calculable coefficient here that is in the notes. These are directly the Wilson coefficients. And I'll describe it now in more detail, but for d equal 3, we define this constant, gamma 3 equal alpha 3 plus 2 beta 3. Let me make sure this is correct. Alpha 3 minus beta 3, sorry. Alpha 3 minus beta 3 alpha 3 minus beta 3, okay? And now this is the constant that has been measured in the lattice, and its values are given by this. So this constant is not positive, and here I can quote a bunch of numbers. So we have gamma 3 cross 6, 7, 8, okay? And it has been measured for a number of gauge groups, starting with Z2, which is the lowest one. It's negative, and we'll see in a second why it's interesting that it's negative, okay? And then there are measurements for SU2, which is still negative. For SU3, the measurements were not done with such great precision, but it's compatible with 0. And then for SU6, has been also measured, it's 0.2. And for SU, now you can do an extrapolation, okay, with some power ansatz, power-like ansatz, and you get here at 0.3, okay? And now we're going to see, what I would like to discuss next is another observable, which is the S matrix of this theory, okay? We're going to scatter these Goldstone bosons in 1 plus 1, and our aim is going to try to bound the leading Wilson coefficient, okay? And the leading Wilson coefficient is this parameter gamma 3, okay? And to advance you, what we're going to see is that gamma 3 at the level is positive, okay, by the usual positivity bounds, but then the constant receives loop corrections, and it becomes negative, and we're going to see how we can sharply bound it, and I would like to show you that gamma 3 must be larger than minus 1 over 768, okay? That's what we're going to prove now. This is where we're heading. Yes? Which term? This square root? I haven't proved for you where this is square root coming from. I'll be happy to do it later. But this is just a way to summarize all the corrections all the way to 1 over r to the 7 that come from the Nambu-Goto action, okay? So what you are supposed to do here is, because there are 1 over r9 corrections, you are supposed to expand the square root at large r, okay? But it's not my scope now to prove this square root formula, okay? The only thing that matters is that corrections, non-universal corrections start at 1 over r to the 7, and they are given by this equation, okay? That's what we care now. Now let's describe scattering in this effective field theory. And this is scattering that we've seen in the first lecture. The global symmetries are very similar because we're scattering vectors, but in this case, it's vectors of SON, which is D minus 2. So D are the bulk space-time dimensions, okay? Yeah, I think I said before, but let me remind you. And we're now discussing the scattering of two vectors, okay? And this scattering can proceed in a number of channels, which let me write you very explicitly. Okay. So as we did in the previous, in the first lecture, there are two things here. The first thing is that note that because we're scattering in a line, either T or U are 0. Okay. So we may just put U to 0. okay? There is no scattering angle, and we have two kinematical variables now, S and T, okay? But we have momentum conservation, so S plus T is equal 0, okay? So the whole scattering of these Goldstone bosons can be described with a single, the 222 sector can be described with a single element. What I find beautiful about this example, as such, you can think about it as a, if you wish, as a consistent truncation of a higher dimensional problem. Because you may think, so let's now, let me say it more clearly. As we did in the first lecture, now we go to, to a basis where unitary is diagonal, okay? So we are going to have, let's say, a singlet component times here some projector into the singlet, okay? Let me write it here, you see? Plus antisymmetric, I mean the 3 reps for 2 vectors, no? With some projector, which you can find in the notes in more detail, plus symmetric, okay? Plus symmetric of S, no? So you may think of this as each of them is like a partial wave. You may think in these terms, okay? Because unitary acts diagonal, but what has been simplified here with respect to a full-fledged 4-dimensional problem is that crossing acts as a simple equation now. Because crossing, in higher dimensions, crossing is an equation that relates one partial wave to infinitely partial waves, okay? But here crossing is only going to mix among these amplitudes here, okay? So to derive crossing, what you should do is you do, so we look at a particular process, let's say AB to CD of S equal to AD minus AB to CB of minus S, okay? Now, if you impose the identity on this equation here, okay, what you get is that crossing acts like sigma 2 equal to, it's a symmetric function, okay? And sigma 1 of S is equal to sigma 1 of minus S, okay? So in terms of the reps, so this is crossing. So in terms of the reps here, okay, if we do, let me label the reps with I. So I runs on a singlet symmetric or anti, right? So in terms of the reps, this is a linear problem now. It's some matrix M, which is calculable from this equation here, Mij times Sj of S, okay? So M is a matter of, it's a matrix with entries which are numbers, and of course M satisfies that M dot M is equal to 1. If I do crossing twice, I come back to the same point. Okay? This is general for scattering of ON. This is nothing new. The only new thing is that crossing is particularly simple in this system. Okay? Now, what perhaps is new is how does it translate this low energy universality into our knowledge of the low energy amplitude, okay? Now, you see, you can do a calculation, okay, of 2 to 2, and the statement is that, so let me write the solution, and then I comment on it, okay? So you can take this action, and compute each phase shift. Okay, I hope it's clear to everyone how you will compute the phase shifts, no? So, S of S, it's going to be 1 plus, there is a factor here. Let me get all the factors correct, but it should be like so. Okay. Okay. So you compute with Feynman diagrams M. Okay. So for instance, leading order, you simply insert this, no? A power of Ls, no? Okay. Which comes from this square. Okay. Sorry. Okay. You need to expand the square root inside here, and the leading term is going to be something like dx to the 4 with an ls square, okay? Which is 1 over the cutoff, no? 1 over units of energy square, okay? This is the leading correction. So you see from this equation, it's clear that this phase shift starts with S, okay? And let me fix the units to this, okay? S over 4. All of them start like that, like this, okay? And now there is the first loop correction. And the first loop correction, it's calculable. It looks like so. Okay. So I hope it's also clear. You need to compute this loop, okay? From this term. There's nothing else, okay? This loop is not finite. It's not finite. This loop is not finite. But the counter term, that you get, there's a the counter term. It's at this level of the action, at this level of the calculation, it's not too relevant the fact that you need a counter term because it's an evanescent operator. There's a technical thing going on here, which is that there is an evanescent correction, an evanescent operator, which is the Ricci, and or put it another way, the UV divergence that arises here, it is exactly 0 in shell. You need it. You're working off shell, okay? It's eaten by the Ricci, okay? What? Let's do it. So, no, it's UV divergent because there are derivatives in the couplings here. We're using this operator here. Okay. All right. Now at the next order, okay, it will be 2 loops now from Nambu-Goto. Yes. Yes. I'm normalizing the action, but there's a simple counter term that you need to take into account, okay, to this calculation, which can be fixed by this operator here, okay. Now, here there is a now this is a what is the issue? The issue is that in 2D, okay, this also happens in higher D, okay, which there is a connection between analyticity in the Mandelstam and whether the counter terms are evanescent or not. This connection is deeper than this example, and the fact that you don't have log here, it counts because you get some logs from the S channel plus some logs from the other channel. Let's put here some S, okay, and some factors of 1 over pi, okay. And this ends up giving I, okay? I. So the, okay. It's not ambiguous. There's nothing ambiguous yet. No, no. All right. And then, the next term, okay, is alpha 3 s cube, okay? So alpha 3 again is this term over here. And there's a correction which is alpha 3 plus 2 beta 3 s cube plus dot dot plus dot dot plus alpha 3 minus d minus 2 beta 3 s cube plus dot dot dot. Okay. This term here is unambiguous and is proportional to d minus 26. This is a calculation by Dubovsky. If you want to read more about the calculation of this term, about whether it's ambiguous or not, it's Dubovsky, Flauger, and Gorbenko. And there's a beautiful story behind it that I'm not going now to make justice to it because my interest is to discuss as matrix bootstrap here today, but the fact that it's d equal minus 26, it's a reflection of the fact that the strings are critical in d equal, bosonic strings are critical at d equal 26, okay? And the way you see it in this, system is because all the one loop corrections are universal, okay? Regardless of the number of external legs, okay? And what you see in this calculation is that if you compute 2 to 4, okay, and there is no operator that you can write down in the action that contributes to the 2 to the 4, okay, at this order, okay, and this term here is proportional to d minus 26, okay, and the relation here is that exactly at d equal 26 there is no particle production, okay. And it turns out that you can guarantee the no particle production to any order in perturbation theory once you have fixed once you cancel this particle production here by switching the right amount of degrees of freedom, it's like an anomaly, okay? Then you are fine at all orders and there is no particle production, okay? And there's a whole story behind which, because there is no particle production, all the scattering is in 2 to 2, or n to n factorizes into product of 2 to 2, okay? And I don't want to say more because this will bring me to another story, okay? But just be aware that there's a beautiful story which you can start reading from this paper, okay? What I wanted to say, so now let's go to the simplest case. So the simplest case is d equals 3. So this is for general D. When I say D, I hope it's clear now that I'm referring to the capital D, okay? So the number of bosons. So for D equals 3, it means one boson. And now the 3 channels collapse into one channel, so it's even simpler, okay? And in this case, we don't need to use the reps because we only have one Goldstone. And the phase shift simply looks like S over 4, okay? Now you see, this guy cancels, so there's also some criticality in D equals 3. And then we get this term here, which is alpha 3 minus beta 3, which I may just call gamma 3, okay? Gamma 3 S cube, plus further terms, okay? So now our goal, it's clear what I'm saying now. I'm only scattering a single Goldstone, no flavor symmetry in 1D, okay? And we have this term plus this term, okay? Plus some two-loop correction, Okay, there are a number of different loops. One of them is this one. The contact term, it's from this non-universal operator, okay? Which gives this correction here. Okay, so now we would like to bound this operator. So let's do it. Let's switch to the S matrix. Sorry, let's switch to the M matrix, okay? Using this identity here. So M matrix of S is equal C2 of S squared, our famous operator in these lectures, plus 2 gamma 3 S cube at 3 level, at 3 level. And the full-fledged MS, which follows from this phase shift at 2 order S cube, okay, it's equal to C2 S squared plus I C2 squared S cube over 4. So this one loop, okay? And we see again what I said before, that it's imaginary. This is how we detect the presence of a loop, but there is no lock for the reason I was saying here before, okay? And then we have the two loop correction plus the 3 level from the higher dimension operator is C2 cube over 24 S4 plus order S5, okay? So this is the calculation at the, if you wish, the exact, okay? Okay, so here, and now we run the arc argument, okay, that we did the other day. So we can define an object, which is 2 over pi, from some epsilon to infinity, im of m of z over z cube, dz. So this is simply C2 plus order epsilon, positive, okay? And then we have A4, which is 2 over pi, from epsilon to infinity, im m of mz over z fifth, dz, which is z2 squared over 2 pi epsilon plus C4, did I define it somewhere? Yes, C4 is here. Give me a second. It's this coefficient here, 2 gamma 3 minus C2 cube over 24, okay? Plus order epsilon, okay? So maybe I should be more detailed. It's clear to everyone, these equations. Here, okay? Okay. But now, here we see that at loop level, okay, we are informed at loop level that gamma 3 can go negative, right? Because there is this running of gamma 3 with an abuse of language, okay? We may think of this as a running, okay? Which is larger than C2 squared over epsilon, okay? There's some factor of pi, plus order epsilon, okay? So you see, if we go to small epsilon, clearly gamma 3 can probe negative values, okay? But by how much, we don't know, right? Because it's an IR-dependent quantity. It's hard to establish a sharp bound on gamma 3. This equation all informs us that even though at tree level it may look positive, because at tree level we don't get neither this, okay? At loop level it probes negativity, okay? And now I'm going to show you how to derive a sharp bound, which is going to be this bound over here, okay? Is it clear, the motivation? And then we'll do it for the multi-flavor case in this lecture. And then I will explain how these ideas generalize to higher dimensions, to full-fledged higher dimensions, so scattering of pions. Okay? All right. So let's derive here the sharp bound, okay, on gamma 3, which is the first bootstrap bound that you are going to see in these lectures. So the point is that, so we are doing a scattering, no? Remember, on the S-plane, no? And here we have unitarity, right? And S of S, okay, it's a map from the upper half plane to the unit disk, okay? Or to the inside of the unit disk. So here we can have S equals 0, and this is S equals 0, right? So some physical S matrix is going to be something like this, okay? It maps inside, because we know that S of S is more or equal than 1, okay? Now, actually what we would like to do, you see, we would like to bound the derivatives of S, okay? Where S is this nice holomorphic function that goes from the upper half plane to the unit disk, okay? And for this, I need a couple of small theorems. The first one, which I'm sure all of you have seen in one way or the other, is that this, so these are holomorphic function in the upper half plane, okay? Or we may think of it as a function inside the disk, okay? And any holomorphic function acquires its maxima at the boundaries, okay, of its region of analyticity. So intuitively, you think about holomorphic functions as these smooth functions that the maxima or minima are on the boundaries, okay? And this intuition actually comes from Cauchy, because you may write the function at any point, you may write it as the average of the function in the neighboring points. So because at that point, at any given point is the average, the maxima can only be attained in the boundaries, okay? That's an intuitive way of seeing this result. So you may just write dw over 2 pi I, dw, I take a small contour around w minus z equal epsilon. So more explicit is 1 over 2 pi, d theta over 2 pi, f of zeta plus epsilon I e to the I theta, all right? So we should remember this. The holomorphic function acquires its maxima at the boundary, because at any given point is the average of the surrounding points. And now we do the following trick, which is a so-called Schwarz peak trick. Schwarz peak, okay? So what is the trick? The trick is we build this new function. Let me call it, out of the holomorphic function, we build a new holomorphic function, okay? Which I call f1 of z, and I define it like so. I define it as, okay, this is a bit a heavy notation, but it takes the function f, this delta 1, and it's a function, you should think of it that it's holomorphic in z, and depends on some parameter, w, which I'm going now to define. And this is defined as like so. It's defined as f naught of z. So f naught is our original function. I'm introducing this notation because we may want to then do some iterations. But f naught is our original holomorphic function. okay? Minus f naught of w over 1 minus f of w bar, well, the naught, f of z, okay? And it's divided by this, z minus w, 1 minus z w bar, okay? So you see, this new function has very much the same properties at f naught in the following sense. The function, it is still analytic, okay? So W is a point in the, so now I'm describing maps from disk to disk, and W is a parameter inside the unit disk, okay? So you see that any singularity in this ratio is canceled by this ratio here, okay? The way it's built, okay? So even though W is a parameter inside the unit disk, this function still has no singularity inside the unit disk, okay? So we are still talking about a holomorphic function, okay, inside the unit disk, okay? And now it's not hard to check by yourself that this is also bounded by 1 in the unit, it's bounded by 1 at the boundaries. Very much so like the S matrix, okay? Okay. So the reason why we are building this finite ratio is because now we may take z and w to be very close, and what this achieves is to bound the derivatives of the function, okay? So from this construction of a Schwarz peak, what you learn is that not only the function, the holomorphic function, also its derivatives inside the holomorphic domain are bounded, okay? That's the idea. So, any question here? So what is so that's the result, no? F1, so if we start with an F naught of Z, let's say, which is bounded by 1 around the boundary of the unit disk, then so it is that F1, so let's think of this as the S matrix right away, the S matrix that we are computing. S1 of Z is also bounded by 1, okay? And now you may ask, well, and what is the function that saturates this bound? What is the function that is going to give us the maximal value? So for this, what you may notice is that if you pick an S of Z that looks like so you may have some pure phase, and then the notation I'm using is Z minus Z naught of 1 over Z naught bar Z, okay? If you plug this into this definition, what you get that it's a pure phase, okay? So S1 of Z, and it's this phase over here, A alpha, which by construction, well, the phase, its modulus has modulus 1, okay? So this is the function that saturates the bound. And now you see, now we can generalize this whole idea, which are called then multi-point Schwarz peaks. So now, because this function also is bounded and it's holomorphic, now we could do the Schwarz peak of S1, which we would call S2, right? And this would be saturated by two products of this. These in the mathematical literature are called Blaschke products. I don't know how to write Blaschke, but Blaschke, if you look for a Schwarz peak, you will find it, products. And in the S-matrix literature, which were discovered sort of independently, are called CDD factors. CDD factors, Okay, so the CD factors are holomorphic rational functions that saturate unitarity. Okay, so what I was saying, if you want now to find a function that saturates, say, further H bar peaks, you will need to take further products of this function. Okay, because the application of each bar peak, the application of each of these operations here reduces one of these CD factors until you hit the phase. Okay. Now, okay, this was a piece of mathematics that I had to very basic thing about complex calculus. But now you see our problem of the one-dimensional flux, one-dimensional Goldstone boson fits into this mathematics. Okay, so now we can apply these ideas to bound gamma 3. Okay, and this is what I'm going to show you now, which is a straightforward application of this. So we take basically this equation here, okay? Actually, I could discuss it slightly more general, the story. Any question? Okay, well, now we are supposed to plug here this phase here, okay? And what do you get? So a nice way to do it is that we do Ix, Iy, okay? So I'm approaching the real line from here, from the imaginary axis, okay? And we can do so because, as we have analyzed from the effective field theory, at the order that we are working, namely one derivative, there are no non-analyticities. So we expect the first derivative to be well defined. Okay. Okay, and if we plug the phase, if we plug this phase into this equation, what you will get is -1 plus 1/96 plus 8 gamma 3 x times y. Okay. Plus higher orders, which must be smaller than 1. Okay. Let me write it like this. So this, and then this. Okay. I already took the imaginary part. Okay. Okay. So this follows from this equation over here. Okay. So then, all in all, if we now solve for gamma 3, okay, what we get here is gamma 3 is larger or equal than -1/768, okay? So we learn two things. We learn what is the maximal absolute value for gamma 3, okay? And we also learn which is the function that will give us, which is the S matrix that will give us the maximal value of gamma 3, and this will be a function with a single resonance, okay? Now this bound was obtained before the lattice simulations, and then nicely enough, the lattice simulations, which I already erased, obtained values that were compatible and in some cases close to the extremal value. Okay? Now, this is what I'm calling the simplest example of an EFT bootstrap, which allows us to bound, optimally in the 2-2-2 sector, the Wilson coefficient in the low energy expansion. But now what I would like to show you is that as soon as we complicate slightly the problem, we don't know how to solve it anymore, okay? And then we need to switch to numerics, okay? So the reason why here the problem was so simple is because it was we landed into complex calculus of one variable, okay? But you see, as soon as we start having several Goldstone bosons, now it's not anymore, now it becomes a vector valued problem, okay? And this problem is hard to solve. But we may still do some progress by taking crossing symmetric linear combinations, okay? So before I was arguing that crossing symmetry acts like some matrix that mixes the various reps, okay? But we may hope to apply this idea of which-bar peaks if we take a linear combination that is invariant under crossing, because then we have the same type of problem. We have a function of one variable, which is bounded in the whole real line, and analytic in the upper half plane. Okay? So you can do so. You can take, for instance, these linear combinations, singlet minus anti. This is an exercise for you. You can check that these linear combinations are invariant under crossing symmetry. This is indeed equal 4 now. Okay? Namely to O2, okay? Or SO2. Yeah. So I'm going to code now without proof, but basically the idea is clear, no? You take these linear combinations, okay? And now what you are supposed to do is each linear combination, you should plug it into this equation, okay? And expand at small s using the calculation from the effective field theory, okay? And this is going to provide you a bound on alpha 3 and beta 3, okay? So if you do so, you obtain the following. You're going to have 3 linear bounds from the 3 equations. And it looks like so. It looks, you get alpha 3 larger or equal than minus 1 over 768 plus a calculable factor. And then these lines here are at the point alpha 3 equal minus 1 over 768 plus modulus of beta 3. Okay, this gives you 2 lines. These 2 lines over here. Okay, so from this calculation, you learn that this is the allowed region, allowed. Okay, okay, and this is beta 3, alpha 3. And this now, let me see that now this is for 4-dimensional flux tubes. Okay. Here we don't have measurements of these constants, but they must live in this space here. Okay. But this is not the most optimal thing that we can do, because we're only exploiting a slice of crossing by taking these linear combinations. Okay. Crossing contains more information. So now we need to switch to numerics to solve this problem. And I cannot do numerics in the blackboard, but I'm going to describe how you would do it, okay? So the idea of the numerics is that, well, there are a number of approaches. Let me describe one. So what we're going to do is that we're going to solve for crossing now, and then we will impose unitarity numerically, okay? We'll solve for crossing and for analyticity at the same time. How can you do so? So consider these ansatz. Sigma 2 of chi and sigma 3 of chi. So I do an expansion of chi to the n, Cn of chi to the n, an minus I bn chi to the n. So now let me explain what these equations mean. So chi is a Moebius transform of this type, Si, S plus I, okay? So what this does, I think I have some pictures. Okay. Sorry, let me write it better. Well, in the normalization that I'm using, it's actually 4 minus plus A and 4 minus IS, okay? So what this does is, so these are functions of S, secretly. Remember, these are the various channels that I wrote at the beginning, sigma 1, sigma 2, and sigma 3, okay? And remember that sigma 2 had to be crossing symmetric. Sigma 2 of S is equal to sigma 2 of minus S, okay? But you see, this K of S achieves so, okay? K of S is crossing symmetry, okay? So I'm doing and then what does K of S? K of S is a conformal map from the upper half plane to the unit disk, okay? So here we have S equals 0, and here we have S equal infinity, okay? And here we have S equals 0, okay? So this is the S plane, and this is the chi plane, okay? So you see, if we impose that our function admits a Taylor series in chi, okay? By this, we're implicitly assuming that it's a convergent series for chi smaller than 1, and by the conformal map, the whole inside of the chi plane is the whole upper half plane, okay? So the very fact that our sigma 2 admits this expansion encodes analyticity in the upper half plane, okay? And similarly for sigma 1 and sigma 3. Now, crossing for sigma 2, I already mentioned. Sigma 2 is equal to sigma 2 of minus S. And remember from the beginning of the lecture that sigma 1 of S is sigma 2 of minus S, okay? And this I solve it by taking these linear combinations of coefficients, okay? Maybe I can be more clear here. I'm solving for crossing and for real analyticity, okay? All right? So, okay, we have solved two of the constraints, which were analyticity and crossing. Now we are left with unitarity, right? And now unitarity is hard because there's always this clash between crossing and unitarity. Why it's hard? Because why is unitarity hard in this basis? Because, let me give you an intuitive reason, which maybe I have not made explicit enough. When we go to the unitarity basis, okay, let's look at one particular channel, S of I. The function is bounded by unitarity for S larger than 4, S larger than 0, okay? Whereas I is a linear combination of these functions here. But on the other side of the cut, okay, it's not bounded directly by unitarity, but it's going to be some linear combination. You will get, let's say, let me make an example. So S singlet of minus S, let's say on this side here, it's going to be S anti of S, S symmetric of S. So you see, the function here is bounded, okay? Because each component here is bounded, but we don't know how it's optimally bounded, okay? Actually, what you can prove and check is that the optimal solution, of course, is going to be 1 here, okay? Now, by the EFT, it's also going to be 1 here, okay? But elsewhere, in the negative axis, the amplitude can go above 1. And actually, this equation would predict that it can go up to 2, the modulus. So it's a hard problem to solve. Okay? Yes? Yes. Yes, but we don't. This is true. We're using that, but we don't need to claim so many heavy machinery. We are only we are simply using that we can. Yeah, we are using that. Any holomorphic domain can be mapped into the unit disk. Okay. Yes. All right. So you see, it's hard to solve analytically. Perhaps it's possible, but we don't know how to do it at the time being. So we're going to do numerics. So the numerics is going to be the following. You take these ansatz, okay? Maybe one comment is in order. Remember that yesterday I was talking about dual versus primal optimization, right? So let's think here on the range of alpha 3, right? Remember yesterday we're doing C3, right? We're playing a very similar analogous with a 4-dimensional problem. We're looking at C3. We're looking at C3 over C2, remember? Okay? And we posed a primal problem, which was to minimize this object. No? And then we derived a dual functional, which we were maximizing to achieve the minimal value of C3, right? Here, it's exactly the same story as any optimization problem, but now I'm describing the primal version of the story, because I'm directly building an ansatz for the S matrix. To make an analogy with respect to yesterday, it would be as if in the primal formulation of this problem, we would do an ansatz for the partial waves. And we'll look in the space of partial waves and minimize C3 as we vary the space of partial waves, okay? So we are building from inside. We're building S matrices that are valid modulo the constraint of unitarity, okay? So what do you get? You get a function that looks like so. You get the solution of the problem gives you this. It touches optimally here, okay, which is this bound over here. And then it asymptotes to these other analytic bounds, okay, for large positive or large negative beta, okay? And now this is allowed region, okay? Any questions so far? Maybe I should say one more comment, which is, let me write it here. This is actually a fun exercise that I encourage you to do in Mathematica. It's 5 lines or so. Maybe I will put it on the notes, okay? By the way, yesterday night on the notes, I added a small Mathematica code to do this dual problem I explained yesterday, okay? So, and it's ready to use. You can just copy in your notebook, Shift-Enter, and it will split you the number, okay? So, let me make one more comment here to derive this curve, because it was a bit fast. There are two parameters here that control the accuracy of the numerics. One is how much freedom are you building in the ansatz, which is controlled by this sum here, how many coefficients we include in our S matrix parameterization. And the other is you need to impose unitarity. So from here, we'll go to the reps, okay? And we will impose that they are smaller than 1 for S positive only, okay? And here we need to take a grid of points in S, okay? Of course, you can do it slightly more clever and work directly on the chi plane, on the chi circle, and do a grid of points around the circle, okay? But there are these two parameters, how nmax and the grid of unitarity. And basically, you want to always keep a very fine grid. This, if you keep, for a fixed grid, if you increase nmax, eventually you're going to leak into a non-unitarity regime, right? So that's how these parameters work, but it's a bit of an art, but with a bit of trial and error, you can just make it converge nicely, okay? And perhaps I should say that in the same way as I described yesterday, this problem admits a dual formulation that gives you curves here on this other side, okay? And then there's a small gap, a small duality gap, that is insignificant, okay? It's small and we can make it arbitrarily small, pushing the numerics. So in this primal version, we are filling in S matrices from inside. So we are filling in the allowed space, but we'll never be sure whether we have explored nmax large enough, right? So you may always have this question about whether by working more, you can lower this curve, right? So that's why the dual formulation in these examples is nice when you do numerics, because then you can bracket from both sides. On one side, you build the S matrix, okay? And on the other, you make sure that you will never be able to find an S matrix that does it better, okay? So here is the primal discussion. In the notes, I give you literature to look for the dual formulation of this problem, okay? But this is nice because now we can look for the generalization of this into higher dimensional problems. Let me make one more comment before I move on to higher dimensions. Just to make a bit more of justice to the phenomenology of flux tubes, which is the following observation. When we solve this problem, we get the maximal value we get the extremal values of alpha 3 and beta 3, but in doing so, we also get the values of the S matrix, right? Because the optimization problem splits for you the values of N's and B's. So you can simply plot the S matrix and look how it looks. That's a very nice aspect of the primal approach, that you just get the S matrix. So if you do so, you observe the following. You observe that in the antisymmetric channel, now we are plotting as a function of S, the amplitude along the boundary, okay? And what you see is that the antisymmetric channel, this one over here, has a resonance behavior in the antisymmetric channel. And this is something, and we can measure the coupling, okay? So we can do a plot like this. So I'm moving here in the boundary, okay? Actually, let's put the arrows in the other direction. I'm moving in the boundary. And what you observe is that this resonance has a behavior like this. So this is the coupling or the width, okay? And this is its mass in the antisymmetric channel, okay? So this in the EFT, this is a particle, a massive particle that couples to this operator here, which was 0 by the equation of motion, except if you put another field here. So we are looking at a particle of this type, a square m square anti plus a kk, okay? So as we move around this boundary, we observe the same particle that the lattice observes, okay? And it actually matches the coupling, okay? So it seems like these matrices have something to do with the actual real dynamics of QCD flux tubes. Now I'm going to switch topic in the last 20 minutes, but we are going to, yes. Imaginary parts? Because, yeah, here we are only interested in dynamics that stay in the flux tube. But presumably when you go, I guess you are interested in production of blue balls or something like that? Eh? Ah. We can forget about them because these are because we are low energies here. So all those are heavy states which we're not producing yet. Any other question? Yes. Yeah, it is rings. Actually, maybe I should. Yeah, this plot now it became a bit busy, and maybe I should redraw it better. Okay. So, so it looks like so. There is this line that is this bound over here, okay, and these two asymptotic lines, okay. Now these are analytics, which were simply the idea that we know how to bound derivatives of holomorphic function, and now there are numerics, okay, and now both primal and dual numerics touch here, okay. Actually, there's some sort of conservation of a difficulty, namely in the dual numerics of this problem, we can also solve analytic at this point here with a different set of equations that look very different, but we can also solve analytically. And then yes, the dual looks something like this. It looks like it touches here, and then there is a small gap that can be shrinked as we improve the numerics on both sides. Okay. But I think this is an interesting lesson, no? That now we can take to even harder problems. So there are two interesting lessons, at least. One is that there are some coefficients that from the effective field theory are polluted by IR contributions, but we may still access to them in a non-perturbative fashion if we look at the full unitarity equation, not simply to the imaginary parts of the amplitude. Okay? This is the lesson number one. And the second lesson is that when the problem becomes harder, when we have many partial waves. Here we had we had a consistent system with 3 partial waves, right? Actually, it would be nice to see how this is generalized in the sense that you could consider now scattering higher reps and try to build a more and more complicated system, some sort of dimensional deconstruction of the higher D problem. But when we go to, let's say, plain scalar theory in higher D, we have infinitely partial waves, and there is a formal equation that we can write where, but it's not very useful, at least I don't know how to make it very useful, which will look like this. We'll have SLs, there will be some crazy kernel and matrix that relates partial waves on the unitarity cut with partial waves on the other cut, okay? So this is the heavy, the hard version of this problem in higher D. So there we're going to go directly to numerics. And let me discuss the simplest numerical problem that we could do, okay? So let me make something very clear. So this was the simplest problem that we could solve, and it was D equal to, okay? Now I'm switching, but I'm taking some lessons from this example, some moral lessons, and I'm going to the simplest bootstrap in D equal, in space-time D equal 4, okay? Okay? It's clear? Hope no one gets confused now between target dimension and space-time dimensions. Okay. So Now we may look again at our favorite EFT that has been appearing again and again, and we look at the scattering, at the elastic scattering, P1, P2, P3, P4. Okay? And now, as we showed, we could parameterize this amplitude by some Taylor series around the analytic region, no? And we were able to derive some bounds yesterday. C2, square, and so on, okay? But now, what we like to do is to bound right away this operator, these coefficients, using the same strategy, okay? So what do? We build an ansatz to solve for analyticity and for crossing, which follows very much the same logic. So we'll have a function. Now we build an ansatz which looks. I'm here presenting the simplest version. Then I can give you reference about improvements of this idea. Okay? Alpha, beta, gamma. Okay. Rho S, rho T, rho U. Okay. Okay. Where this is a symmetric tensor. Okay. Okay. And these rho are they play the same role as the chi variables. Okay. So what do? So now we look at the amplitude as living as in this space, in the direct product of the S Tu, okay? And at the end of the calculation, we pick a slice which is S plus T plus U equal 4m squared. This is how we are planning to solve crossing. Completely analogous to what we did in the system over there, okay? But now the rho function, I'm not sure I have it, but it's a non-crossing symmetric function, which will look like this. It will look 4 minus S naught, 4 plus 4 minus S naught, minus 4 minus S plus 4 plus S. Okay. So this is an exercise for you, which is nice to do. So consider the S cut plane with a cut here, and check that this is a map from this plane into the unit disk, okay? Where we have rho here, S here, and then we'll have that points in the upper side of the cut are mapped in the upper plane, in the upper side of the disk, okay? Are mapped to the lower side, okay? So we are opening up this discontinuity and mapping the whole plane in the unit disk, okay? So now this ansatz solves both things at the same time. STU symmetry, okay, and analyticity. Okay. And now again, we have, well, in this case, we have three numerical parameters appearing into the problem, okay? Because we have partial waves. So we're going to have the n max for our cut our cutoff in the ansatz. But then we impose unitarity by generalizing unitarity equation with partial waves. Okay. So we are going to have now some partial amplitudes with the definition I gave you the other day, which depend on S via this equation here, okay? And are also a function of this tensor, okay? Alpha, beta, gamma, no? Gamma. I defined in the previous days how you decompose, no? I'm using the same formula. And these partial waves are bounded by 1 for S larger than 4, okay? 4m squared. Okay. And we should impose this for L equals 0, 2, ... up to some L max. Okay? So here we are in the realm of numerics, but that's life. When you want to ask more interesting questions, often you don't know how to do analytics. And it's controlled by these three parameters, L max, N max, and the grid. Okay, let's call A grid. A grid. Okay, so with a bit of trial and error, okay, you can get some nice convergence as you send these parameters to very large values, to virtually infinity, okay? And now what is the rule of the game? The rule of the game is that we're going to ask physical questions to our S matrix, okay, subject to this constraint, okay? So one such question now is, what are the min-max values of C0 and C2, okay? So what do you get if you do so? You get the following. I think I have a plot, which I'm going to draw in the blackboard. So here I'm plotting C2 over 32 pi. And here I'm plotting minus C0 over 32 pi. Okay? So it looks like a leaf, okay? It looks something like this. Now, of course, we recover the usual positivity bound, okay? Okay. Here there is roughly 2, and here there is roughly 0.8, and here there is roughly minus 6, okay? To give you a sense of the... And now all this whole region is allowed, okay? And wherever is outside is excluded, okay? Yes? What? A grid? Yes. A grid is the fact that it's a spacing, okay, in S that we are using to impose unitarity in a computer. So this is a numerical problem, but it's very simple, right? I'm describing here all the elements. Take these ansatz, we solve for crossing kind analyticity, write this in a computer, okay? Write this in Mathematica, for instance. And now do some min-max of some observable subject to this constraint, okay? And this is now an example where I min-max over C0 and C2, okay? And again, a nice aspect of this approach is that it splits for you also the S matrix. So we know the S matrix around the boundary because we know the values of alpha that come out of this optimization problem, okay? Now, what I want to say, well, of course, we get the C2 equal positive, okay? Now, here, in this normalization, okay, this is a theory which has like negative quartic, okay? So like it would be like a theory with a cosinus potential, okay? The theory here. And here is the lambda phi 4 theory, if you wish. Because as we know, C2 is proportional to the imaginary part. So if the imaginary part is small, okay, we are weak coupling. So all the theories here are weakly coupled. And now as we move here, these are theories that are maximally strongly coupled all the way to particle production, okay? Now, let me give some reference, and then I'll make a few more comments. I'm not sure I have some references here. So if you want to read more about these numerics, this bound on the range of C0, okay, so C0 bound, you can read more in this archive paper, which contains all these equations, okay? Now, if you want to learn more about the dynamics of the S matrix around the boundary and well, this whole plot, this is obtained in a couple of papers. which is 0.71244.8, and 2210.01502. Okay. This, if you want to stare at these plots, a better version of these plots than the one in the Blackboard. Now, with this, I'm heading towards all what I wanted to say. I would like to point, I would like to mention, maybe I can make a very quick comment about the recap. So this higher dimensional version of the S-matrix bootstrap that I described now, it's the topic of active research, okay? And there are some generalizations of what I have explained here. So let me give you 3 papers, which is, if you wish, examples of things that you can now do, which are pretty recent. So there's a nice paper that studies glue balls. Okay, so the ansatz is morally very different to the one I wrote. Okay, but now you can include also poles in the ansatz due to the exchange of glue ball resonances, spin to resonance, and so forth. And this is a recent paper, well, not so recent anymore, from 2 years ago, 00127. Then to make connection with our discussion of the black disk scattering, you can also try, for instance, to maximize other stuff. Instead of low energy constant, you may want to take this approach to maximize the cross section in the DBUV. So there was a paper last year that did so, in case you are interested in looking at it. And to give a sense of the fact that this is an evolving field, just today there was a paper, okay, 145, okay, which is about primal 4D, okay, which is a version, it's a version of this problem, okay, but improved, okay, improved in the sense that here we have been a bit naive with unitarity. We know more about unitarity than this, and this paper of today incorporates further aspects of unitarity into the primal approach to the problem. Okay, and I also suggest that you look at reference inside here if you want to get a better feeling of the field. So, so to conclude, okay, as a roadmap of the logic that we have been following, what we have seen how to exploit positivity, okay, causality and locality to bound effective field theory coefficients in weakly coupled effective field theory, okay? And then it became a bit more technical when we put towards crossing, but we managed yesterday, okay? We put crossing constraints. And this as far as we could go for weakly coupled effective field theories. And then we switched to these examples where, where we saw that if we impose full unitarity, we can go further, okay? And then what we saw is that parameters that from the dispersion relations are not bounded by unitarity, like C0, the C0 coefficient, are however bounded. And to bound them, you need to switch into these numerics, okay? So what I expect is that in the future, these methods will become closer and closer to theories that we care, okay, by including particles with spin, more refined versions of unitarity, like this paper of today, and perhaps more detailed comparisons with lattice, like this paper, or the one of flux that I discussed. So I'll leave it here and I'll take questions. Thank you. Yes?